Welcome to SAR 3. Our next talk is called Hacking the Universe When Strings Are Super and Not Made of Characters. It's going to be held by Robert Helling. It's a talk about physics and the ideas about the nature of space and time, and the answer to the ultimate question of life, the universe and everything, I guess. And I'm very excited to hear about that. Please give a round of applause to Robert.
Hello. Before I start, I wanted to thank a number of people, mainly you for coming. Oops. Since this is not on the main track of the conference and you're still awake on day 4 to hear something which is slightly off topic, but I hope to convince you that it's not so off topic at all. So, usually I speak in front of other audiences, and I don't know most of you, and probably you don't know me. So, before I do this, so first I'm going to introduce myself in 1 or 2 slides, and I decided to talk about 3 particular subject areas, and this gives you the 3 main parts of my presentation. So the first, I talk about cosmology, which is that part of physics which deals with the universe as a whole. Then the second part is about particle physics, and I guess all of you have heard about LHC, that eventually finally came up a few weeks ago and is now, well, after the winter break, about to take first data. And then the last section is about string theory, which is a proposed theory you might also have heard about, that is there to unify gravity and quantum physics. And when I introduce these 3 topics here, I should say that my own area of expertise is this. I'm a string theorist, but I've also worked on cosmology. I have not worked on experimental particle physics, so this part is, I read this. I'm not actively working on this. And I finish, maybe with, if I have time, with some speculation on whether it's possible to have open source physics. So, who am I? My name is Robert Helling. If I don't use my real name, I use my other name. I do research on string theory and a number of other things. I work at Ludwig-Maximilians University in Munich, and I've been at some other places, and in the net you can find me here. To introduce myself, this was my first computer. This was the first computer that worked. This was my first modem, and it didn't work because this was our telephone. And you see, round, not round. But I was introduced to this, and from that time, I was taken. So, why am I here? Why am I speaking about hacking the universe? And that is because I'm deeply convinced what we do when we do physics is also hacking. So what is hacking? Let's go to the jargon file. Who's a hacker? A hacker is a person who enjoys exploring the details of programmable systems and how to stretch their capabilities as opposed to most users. Well, if you forget about programmable systems, this is pretty much what we're doing. We're trying to explore the details and stretch the capabilities of what the world offers to us. And in particular, it also cites RFC 1392, where it says, a person who delights in having an intimate understanding of the internal workings of a system. So, and that's what we do with the universe, and its parts up to the smallest scales. And the other slogan I copied from Make magazine, if you can't open it, you don't own it, and of course we want to own our world. Okay, let's start with the first subject, which is cosmology, which is about models of the world. And I always start with saying until the 1960s, this was mainly speculation and guesswork and broad extrapolation of something you know what you do in the lab to very large scale. So it brings you to pictures of the world that are only quantitatively better than this one with the Earth on number of elephants on a turtle. Yeah. So, but now I'm going to move forward to a little bit later. I mean, this is a very recent picture, but in the 60s, people discovered, had similar things, not with this fidelity. This is a picture of the Hubble Space Telescope, where they pointed the Hubble Space Telescope at an empty area of the sky. So there's no star in this picture, at least when you look at it with your bare eye. So they pointed the Hubble Space Telescope into a dark area of the sky and looked at it for 48 solid hours. And this is what they found. And every little dot here is a galaxy, right? And this is pretty much as far as we can see in the sky. And we have good understanding what's going on here, all these little dots. And I would particularly point to the dimmer, redder ones. These are the furthest away structures that we can see in the nearly optical spectrum. So this is what we see of the universe. This is the universe. And when we look at these pictures, people discovered, namely Hubble, that you just not look at the pictures, but you do measurements. And two things you can measure with some tricks I'm not going to explain is first a star's or a galaxy's distance, and another thing you can actually more easily measure than this is the star's velocity relative to us. This you see from the Doppler shift and looking at the star spectrum. And what people found is that roughly the star's distance is proportional to its velocity. So the further something is away, the faster it moves away from us. And to explain this, there are two possibilities. First is we're in the center. Not very likely. Possibility two is the universe as a whole is expanding. But still looking at these pictures, this is not really, doesn't say everything. For example, it could be that the universe is constantly expanding and has been doing this forever. And matter is created out of nothing when the space stretches. That was a serious theory in the 1960s. And its contender was the Big Bang theory, which says, okay, this hasn't been going on forever. There was a point in time where everything was together, and then it exploded in a huge bang, and stuff has flown apart. But how can you tell? From these pictures. Well, let's go to New Jersey, 1965. People were experimenting with the first telecommunication satellites. This is a picture of an early telecommunication satellite. You see people here. So this is just a big balloon, which is with metal coating. So what they did is they just flew this in the air, very high, and then pointed a radio transmitter towards this thing, and on some other continent, they tried to receive the reflected stuff. So it's completely passive. There's no electronics here. That was telecom satellites very early. And this is the antenna that they used to pick up the signal. This is a huge microwave antenna. And this was constructed by people at Bell Labs. That's the Bell Labs of Kernighan and Ritchie. And they had a problem. They couldn't get rid of some noise in the antenna. Whenever they pointed it to the sky like this, there was some residual noise, and this noise is measured in temperature. They measured a noise temperature of 3.3 Kelvin. And they were tuning everything. They were removing the pigeon leftovers from the antenna with still noise. They couldn't get rid of it. And then they talked to people at Princeton University, and those people, the physicist in Princeton told them, actually what you see is not noise. You see the Big Bang. This is the afterglow of the Big Bang. It's the heat radiation that's left over from the Big Bang, which has cooled down to this temperature. And people had speculated about this before when they thought about Big Bang theory. And these people, Wilson and Penzias, discovered this afterglow. They got a Nobel Prize for this not too long ago. And then people precisely measured this, and they discovered it's the most perfect black body spectrum that you can find anywhere. It's absolute thermal radiations coming from all directions in the same way. Only the number is actually 2.7 rather than 3.3. Okay, and then they sent up satellites to measure this radiation, and what they found is that basically the temperature in all the directions is the same. Well, and they made maps of the temperature. This is this is the night sky, if you like. I mean, 4 pi squared. And you see that there are some areas where it's a bit hotter and some area where it's a bit colder. But this is 1 part in 1,000. So how does this come about? Well, the solar system is not at rest with respect to this radiation, but it's moving towards this direction, and therefore there's, again, this Doppler shift. Doppler shift, everybody knows what Doppler shift is? This is the effect that when an ambulance comes towards you, you hear a higher tone than when it's moving away. So when you're moving towards the radiation, it looks slightly hotter, and it's this direction. So if you subtract this movement, you get this picture. Hello, this picture. And you amplify, of course, you always amplify the fluctuations. And then you still see here, this is the Milky Way in the foreground, and you can remove the foreground to end up with this picture. This picture got another Nobel Prize, because what you see here are the tiny temperature fluctuations, 1 part in a million, in the afterglow of the Big Bang. And there are some areas which are slightly denser and therefore slightly hotter. And these are the points where gravity attracted and then galaxies form. So these are the earliest pictures of galaxies. This satellite was COBE. They sent up another satellite called WMAP, which did a more precise measurement here. Looks like this. So these, again, are the same fluctuations, just with better resolution. In the past months, they launched another satellite called Planck, which is going to improve even more on this picture. So I mean, this is a nice picture, but this is not the data here. I mean, we are not looking at a particular spot and then trying to pinpoint the galaxy on the Hubble Space Telescope picture that corresponds to this dot. But what you do with this thing is you basically Fourier transform it, and this is the important graph that everybody draws when looking at WMAP pictures. So what is plotted here is the amplitude or the power of the fluctuations plotted against kind of log of the scale of. I mean, these are the largest fluctuations angle-wise, and these are the smaller ones. So you see there's a peak here around 200, which is roughly the opening angle of 1 degree. And you see this in this picture as well, because you see grains here. And these grains, I mean, the typical grain size here is about 1 degree. So what you see here, the black dots are the data from the picture on the previous slide. And what you can do is you can come up with a model of how the universe expanded. How much matter there is, how much density, how fast the expansion is, how the cooling works. And then you can fit your model to these data points, and this red line is the fit to the data, and it fits except for the early parts and the later ones. It fits extremely well, and it pinpoints our understanding of the universe. We exact from this model that produces this red line, you can understand exactly what is the average density of the universe, what is the average density of normal matter in the universe. How fast is it expanding? How big were the early fluctuations? So this is the real output. There are 7 parameters in this model, and with this graph you determine these 7 parameters. Okay, so that's state of the art in cosmology, and now that we have all these data points here, cosmology has really turned into an observational science rather than a speculative one. Okay, so this is a sketch of what happened in the universe. So here is the Big Bang, and time is going in this direction. We are here, right? That's us, and here, this goes, I mean, this is not to scale, but this goes back in time, and because stuff cooled when it propagated forward in time, when we go back in time, stuff gets hotter. And you see that here is us, and there's a star, and there are a couple of, I mean, this is supposed to be a photon, so there's light, and there are some neutrons. But when you go back in time, I mean, here the first galaxies form, but then when you go back further in time, at this boundary here, the universe is so hot that the electrons boil off the atoms. So what you see here, beyond this line, is you see the nuclei of the atoms and the electrons separately. It's a plasma. You have freely floating charged particles. And this is where this borderline is where this cosmic microwave background that I've been talking about for the last 10 minutes is coming from. Because when you have freely moving charged particles in a plasma, you cannot transmit electromagnetic radiation because it's scattered from here. So, and at some point, all the electrons found their nuclei, and then only neutral stuff is around. And then from this point on, photons, light particles, can propagate. And therefore, we see this line of last collision, which was roughly 150,000 years after the Big Bang. So a very short time, just 150,000 years. But we cannot see with optical instruments beyond this line because light is not going through. It's opaque here. So we have to use other methods, and here the same thing happens with the nuclei. That it's getting so hot that the nuclei don't stick together, and the individual protons and neutrons fly around in this area, and then even the protons come apart and the elementary particles float around in something that's called quark-gluon plasma. But as I said, we cannot look into this time with optical means. We have to find other ways to get data from such physics, and this is my next subject, which is particle physics. And we try to recreate conditions like here in a particle accelerator. And eventually I will talk about this area, which is where string theory lives. Okay, so let's move on to particle physics. Okay, so as you can imagine, so far we looked at the biggest things you can imagine, the whole universe. Now we want to look at tiny stuff, the inner workings of atoms and other things. So I want to look at small things, and if you want to look at small things, what do? You use a microscope. But you probably all had the same experience in school. I mean, here you can tune the magnification of the microscope, and you learn that it doesn't make much sense to use a magnification that is stronger than 1,000 times. I mean, one of these things is typically 1,000 times, and it doesn't make sense. Why doesn't it make sense? Because you're getting in the vicinity of the wavelength of the light. And you can't observe stuff that is shorter than the wavelength of the light that you're observing with. So a microscope won't work for particle physics. So you want to investigate smaller things, you use something else. You have to replace the light. For example, you can replace it with electrons. This is an electron microscope. Because the electrons, as waves, have much shorter wavelength. And in fact, the higher energetic, the faster the electrons are, the higher the energy, the shortest wavelength. So you can use a bigger microscope, or eventually stuff is too small for the wavelength of this electron microscope. So what do? You increase the energy, you build a bigger microscope, and here it is. That's the LHC. But actually the LHC is just a big electron microscope. Well, actually a proton microscope. They're accelerating protons. But the idea and how it works is exactly like a microscope. It's just bigger because you want to produce higher energetic and therefore shorter wavelength stuff to probe what you want to probe. In this example, you want to probe the inner workings of a proton. So this is the line, it's underground, right? There's a 26-kilometer circumference ring near Geneva. Here you see Geneva Airport, here you see Geneva, Lake Geneva, here are the Alps, right? So that's the scale of things. Most part of it is actually in France, not in Switzerland. But this part here is, the French-Swiss border is somewhere here. Okay, so just a quick reminder of what is the stuff we're looking at. So this is supposed to be an atom. I hope you've seen this before. So an atom consists of a nucleus and the electrons that orbit around the nucleus. So electron here in this picture is the blue thing, and from all we know, the electron is in fact a point-like elementary particle. It doesn't have any substructure. But the nucleus here is made up of protons and neutrons, and these are here, And these, again, are made up of smaller particles called quarks. So at this point, I'm going to tell you each proton or neutron, or nucleon, is made up out of 3 quarks. And we're colliding these guys. These guys fly around in the accelerator. And then we see, but then what collides, as we'll see a bit later, are actually the constituents here. Okay, this was how our ordinary matter is made up, so the stage and the chair you're sitting on. We know about a couple more elementary particles. So here again is our friend the electron. It has 2 cousins called muon and tauon, which are exactly like the electron, just heavier. And they have kind of shadow friends called neutrinos, 1 for each of these guys. So these guys are called leptons, and they're basically heavier electrons, although these guys don't have charge. And then there are these quarks I've been talking about. There are 6 types of quarks, but we are made up, so protons and neutrons are only made up of these 2, which is the lightest one down and up. And again, in a similar way, there are heavier cousins called strange, charm, bottom, and top, but it doesn't really matter for this term. So, but these are all the particles in the standard model, well, the matter particles, plus there are forces. So to all our knowledge, there are only 4 forces in nature. Everything boils down to these forces, except if there's telekinesis or something. But we haven't observed this in the lab. Everything we have ever observed in the lab is explained by only 4 forces. And the main force, I usually have an apple, right? I drop the apple and then say, this is gravity. We all know this. At our scales and at astronomical scales, this is the most important force. And then there's electromagnetism, which is light, but it's also electrostatic forces, magnetic forces. They are all they all come from this electromagnetic force or interaction. And it's mediated, so all the forces come with a particle, and the particle for the electromagnetic force that, for example, keeps the chairs you sit on together is the photon or the gamma ray. So this is everything that governs our macroscopic world, gravity and electromagnetism. This makes up all the chairs and all the chemistry and everything. But when you go to nuclear scales, there are two more forces. First of all, there's the strong force. Remember, there was the nucleus, and it consists of neutrons and protons. The neutrons are not charged electrically. The protons have positive charge. So normally, if there were only the electromagnetic force, they wouldn't stay together. They would fly apart, right? Because they have the same charge. But luckily, there's the strong force, which keeps these nucleons together to form a nucleus. And the photon for the strong force is called a gluon. And then there's another force, because nuclei don't always stay together. There's beta decay, there's radioactive decay, and that's called, for this is the weak force is responsible, and they don't even have good names. They have called intermediate vector bosons, or W and Z. But these are all the forces we know. We're extremely positive that at least at all the energy scales we can reach, which includes everything in this room, these are all the forces. And this excludes, we haven't seen any telekinesis or whatever ways to influence your brain with mobile device radiation. Okay, so I'm pretty sure this is correct. Okay, there's one particle missing, therefore I didn't have a good picture. It's the Higgs boson, and that's why we built the LHC. We want to find this last remaining particle that we know from theoretical investigations should exist. But you can mail order it for $9.75 at particlezoo.com. Well, it turns out this number is wrong by 9 orders of magnitude. Okay, these are all the particles that we know. And this is another picture of LHC. Here you can see Lake Geneva. Here you see the French border. And here you see it's an underground tunnel. And the protons, there are two beams of protons, one going in this direction, one going in this direction. And they meet at 4 interaction points. There are four so-called experiments, 4 detectors, where the particle beams cross, and there are sometimes collisions. What sometimes means I'm going to explain in a second. There are 2 big experiments called CMS and ATLAS at opposite ends of the ring. So you always want to have more than one experiment because you want to double check the experiments from the other groups. So these are different detectors. They're not, I mean, different people build these different detectors using different design ideas. So you can always double check the physics. You don't want to build 2 of these rings. They're too expensive. You just want to build 2 experiments. And there are 2 special purpose experiments, LHCb and ALICE, that I'm not going to cover. So my dig is bigger than yours. So a 27 kilometer circumference. It's 50 to 175 meters below the surface under Switzerland, France. There are 2 beams of protons, and each has 7 TeV. You should say, ooh, because that's a big number. That's about an order of magnitude bigger than than the previous accelerators. Yeah, so that is 7,000 times the energy you need for the mass of a proton. So in one collision, you could energetically produce 7,000 protons. Okay? So, and to keep the protons not running on a straight line, but on a circle, you do this with magnets. So there are 1,232 dipole magnets, and you also want to focus the beam. So the beams are roughly 2 millimeters diameter. And you could see the pictures of the beam profile in Fei's talk yesterday, where he talked about the black holes. He had a picture from the control panel. And there are 392 quadrupole magnets, and these are all superconducting magnets. So this is a big technological obstacle. Because they're superconducting, you have to cool them. You have to cool them to 1.9 degrees above absolute zero. And to do this, you use 96 tons of liquid helium. That's kind of the same order of magnitude of all the helium that's produced in a year in the whole world. So there are not only 2 protons in this beam, there are many protons in so-called bunches. So in each beam there are 2,800 bunches, and they go around 11,000 times per second around the ring of 27 kilometers. And so all the protons in the beam are 10 to the minus 9 grams of hydrogen, and they have a total energy of 724 megajoule. That is the energy of 173 kilograms of TNT. But this is all in the amount of hydrogen that you would have in a gas phase at the size of a grain of sand. So this energy is in the kinetic energy in the beam. And that means so many bunches with so many revolutions. That means these bunches cross at the interaction points once every 25 nanoseconds. I've talked about the accelerators. There are order of 10,000 scientists involved from more than 100 countries. So it's really a global enterprise. And the total cost is 9 times 10 to the 9 currency units. Doesn't really matter. Some for the accelerators, some for the experiments. So this is the 10 to the 9. I said they underestimate the price of the Higgs boson. So that's what it looks inside, like a subway or underground tunnel. And in fact, it is an underground tunnel because they use exactly the same digging machines they use to build undergrounds. So here you see this is the pipe, and you see it's slightly bent here. Yeah, that's what it looks in the tunnel. This is the pipe at the surface. So actually what you see here, this thing, I mean, the pipe goes into the picture. This is a magnet. Doesn't look like a magnet, doesn't have the green and red part, but this is a superconducting magnet. So these 2 pipes here, this is where the 2 beams go, beam 1, beam 2, This is where the liquid nitrogen is delivered, and the whole thing produces a magnetic field that's in the vertical direction of some Teslas, which is, I mean, these are also very strong magnets. They're much stronger than all the magnets you see in like NMR at your doctors. Okay, this was supposed to run last year already, but then after 9 days, this happened. So there was a fault in the electrical connection between two of the magnets. So I mean, the electricity is flowing in superconducting wire through all the magnets, and then at some point the conduction was bad and it heated up. So it heated up 100 magnets, quenched, went 100 degrees up in temperature, and 53 were terminally damaged. I mean, here you see the point where it happened. So, I mean, these two things are supposed to be parallel, right? And 6 tons of liquid helium were lost, so the whole tunnel froze instantly at that point. So it took them 14 months to recover, but luckily now, since November again, they're running. Okay, so what do we want to do? I said we want to find this missing particle called the Higgs. We also want to find, there's a theory that all particles that I've shown you on the previous slide have further so-called supersymmetric friends, which are needed for very good theoretical reasons, but haven't been seen so far. But we hope to see them at LHC. And then there are more things. So I didn't put question marks here because I'm pretty much convinced that we will see them once the thing is actually working. And then maybe we see dark matter, which is stuff that we know from cosmology should exist. Maybe we see extra dimensions. Maybe we see mini black holes. And of course, we hope for surprises. I mean, we're doing research. We don't know what we're going to see, right? Dragons. Yeah, I want to have a picture. But there's one thing. Will it destroy the Earth? Especially because of black holes. There's a quick answer: no. And if you want to know why this now, I can come back to this in a Q&A. Okay, this is the pit of the experiment of the, I think this is CMS. So here you see the hole where they bring stuff down. This is there a person somewhere on this picture? No, but I mean, this is one story. You see bottom right. Ah, here's a guy. So you see how big this thing is. So in this pit, they fill with one of the detectors. So how does the detector look? I mean, this one at the surface, the beam pipe goes here. It's taken apart. I mean, this picture was taken when it was constructed. This one, CMS, was constructed on the surface and then lowered into the pit. The other detector, Atlas, was built underground. Here's again a person. So before I explain a bit more how the detector works, I should say, let's look again at the proton. This was the red thing, and I claimed it consisted of 3 quarks. And I was lying when I said that, because actually, when you look at it closer, you see that there are many quantum vacuum fluctuations, and there are about 2,000 particles popping in and out of the vacuum, making up, I mean, these spring lines are also particles that go from here to here, and there are more quarks. They're all in there. It's just the kind of 3 outermost ones that I displayed in the first picture, but we're really colliding things that are made up of 2,000 smaller things. And then we collide them and look at the debris, and this is pretty much like we're colliding grand pianos. I mean, at high energies, we throw 2 pianos together, stuff flies out, and then we try to determine how a piano works. From the debris. But the amazing thing is, people can do this. So this is a simulation of how such a collision looks like. So there are all kinds of, I mean, stuff coming in from here, stuff coming in here, and stuff flying out. And you see it curls up because you put a very strong magnetic field inside these detectors. So anything that is charged goes on a curved path, and from the curve you can determine the momentum, or if you like, the velocity of the particle. There are some uncharged things that fly out directly. So this is a simulation from one of the detectors. So this is the other detector. Actually, I'm going to switch now. Oh, that works. To this little flash animation. So this is the same detector, and now CERN has great. This is at CERN. CERN's great PR website. You can download thousands of pictures and these stuff as well. So as I said, there's the beam pipe. Beam pipe. I said, okay, no beam pipe. Let's do first the tracking detector. So the most inner part of the detector, this is where the collision happens. In this part of the detector, this is filled with silicon. This is basically filled with like the CCD elements of a digital camera, just fill the whole volume. And because then from exactly through which pixel the debris flies, you can determine the track of the particle. So let's try the beam pipe again. Maybe. Yes, there's the beam. So the beam pipe goes here, and now you have two particles colliding, and boom, they go. And different particles that you produce in the collision make it through different parts of your detector. So we've already seen the tracking detector where everything goes through and you record the tracks. Then there's the so-called hadron colorimeter. So anything that's made out of quarks is detected in that part. So let's click on this. So it's this. So basically, this is steel interspersed with, how do you say plexiglass in English? Plexiglass. Acrylic material where tiny flashes of light appear when a particle goes through. So, and these particles get stuck in the plexiglass and also in the steel, and you see how much energy is deposited in the detector from the flashes you see in the plexiglass. And you measure the energy of these particles. Then there's a similar thing for the electrons. They get stuck at this part and get recorded. And then, but most of the structure, here you see, this is just, again, a huge superconducting magnet, because there's only one species of particles which makes it out to this part, which are the muons, remember these were the heavier cousins of the electron. They go through the inner parts of the detector, and they feel this big magnetic field, and then they're detected in these outermost parts. So these two things and the stuff on the outside. And then you can detect where they come up and try to reconstruct the two pianos from all the data you collect. So what do I mean when I should go to the other slide again. Atlas. So we've seen this. Okay, so now for you computer geeks. So the problem is, remember, there's one collision every 25 nanoseconds. So 25 nanoseconds, short time, right? They occur at 40 megahertz. And roughly there are 17 events in each collision. So you have an event rate of a gigahertz. And you have to bring this down to store away. Of course, you only want to store the interesting data. And it turns out most of the collisions are boring because you completely understand them. We're looking for the new stuff. And we only want to store the new stuff. And we expect 1 in 10 to the 7 are interesting. So we want to store 100 events per second. And this is here these are all tape drives, right? Here there's a robot that goes through to put the tape drives into the recording device. So, the big problem is, remember 25 nanoseconds, light traveled 7.5 meters in this time. And remember how big the detector was. So there's already the next collision in the detector long before just light had the chance to travel through the whole of the detector. And all these particles are effectively flying with the speed of light. So at any time, there are always several, the debris of several collisions in the detector just flying out like through the shells of an onion. And and when you do the data processing, you also have to process this data once every 25 nanoseconds, and you want to decide which to keep. So So if you want to read out all the parts of the detector, you read out about a megabyte when you leave on all the zeros, which makes up 15 petabytes per year. And so you can't do this. I mean, this is the stuff you store with this frequency, right? So you have to reduce to 1 in 10 to the, you want to single out the 1 in 10 to the 7 events that you're actually interested in. So you do this in 2 stages. So there's a so-called first level trigger. This is built into the detector and custom electronics, FPGAs, those kinds of things. And you want to pipeline, you want to store the information in the detector for about the time that it takes for the stuff to fly through the detector. You don't want to decide just on the inner bits, or you don't want to have to decide whether you throw away the tracking data before stuff has reached the outer muon detector. So you have to store this, and it was decided it's a good idea to store them for 3.2 microseconds, and that means you always store 128 events. And the way this is done is it's pipelined. So you produce the data, and then it's handed through the layers, and while the new stuff is produced in the inner parts, and at the end in the outer parts.
Question.
Yeah.
If this, because of this high collision rate, there are very high requirements for storage and intermediate processing. Why didn't they just inject less bunches so they have less collisions?
Okay, so the question is, why do they use such big collision rates? Well, we want to see the needle in the huge haystack. So, I mean, we need all those to see the interesting stuff. I mean, we're not going to see a Higgs we're not going to see 100 Higgses per second. We have to take data for years with 100 interesting events per second to dig out the interesting information. So in this early custom electronics stage, the event rate is reduced to 100 kilohertz, and then comes the second stage. Here, all 700 so-called front-end electronic modules, which already collect the data of large parts of the detector, are read out, and the events are reconstructed. That is, the tracks are reconstructed, and data from the energy measurements in these calorimeters is brought together with the tracks, and it's determined what kind of particles have flown through the detector. And you want to boil this down to this data reconstruction stage takes about a second per event. So it's distributed on a shelf, on shelf hardware, so order of 1,000 off-the-shelf PCs, each one dealing with one event for a second and deciding whether to keep it or to store it. And now, at this point, ordinary RAM is also fast enough. It wasn't fast enough in the earlier stage. But still, there's the significant problem because you want to bring the data from 700 components of the detector to 1,000 PCs. And you want to switch the data that goes through, and the data rate is 100 gigabytes per second. So you see there's a non-trivial problem to be solved here. And then there are also tags on the event saying, oh, this was an event with 4 muons making all the way to the end of the detector. And you store it in a grid. So the data storage then is on the top of the Earth, and then it's distributed. I mean, not in the basement where there's the detector, but on CERN ground, and then it's distributed to like 100 institutes all over the world, where people then do offline data analysis with the recorded data. And as I said, data production is about 10 terabytes per day. So you can carry around a couple of hard drives every day. Okay, so why do we do this? I mean, this is fundamental research. This is good for nothing. We just do it because we're interested in how nature works at the smallest scales. But we always have to justify ourselves. I mean, it's interesting for us, and hopefully for you, but if people pressure us, especially politicians, we can point to a couple of things. So we also have our Teflon pens. So first of all, I talked about these magnets. And particle physics helped bringing superconducting magnets from something you did in a special purpose low temperature lab to industry scale. So they needed some thousand of these magnets, and they had to produce them at industrial rates. And now companies can produce these magnets at good fault tolerance levels. And this was the time when also to medical industry could purchase these magnets, and that you find them now in your local NMR scanner when you have your knee injured or something. That you get the magnets from high energy physics. But we have another big business case, and it's this guy. Who recognizes this guy? This one here? It's Tim Berners-Lee. And this is the first this was the first HTTP server in the world. And HTTP was invented by particle physicists because they wanted to communicate their physics data with hyperlinks and pictures and everything, and now you know what happened to this. Okay, so HTTP is a spin-off of high-energy physics. Okay, so this was the second part. Now I'm coming to the last part, my own area of expertise, and I couldn't find good pictures on the internet, so I had to draw them myself. So this is... yeah, so this is a less than 10-minute introduction to string theory. So first of all, what's string theory? So first we have to talk about general relativity, Einstein's, which is really the theory of gravity that Einstein brought us. And the main message is that space-time itself is not just the stage where physics happens, but it's dynamic. So I tried to draw the Earth, the Earth here and the Sun is curving space-time, so I'm trying to draw, and the Earth feels the gravitational force from the Sun because it feels the curvature of space-time. I mean, this is just a picture, don't take it too literally. And it makes the Earth go around the Sun rather than straight line. So whenever you have mass or energy or momentum, it curves space, and this is how gravity works. That's in a nutshell general relativity. So this is supposed to be an apple. These are two flies. This is supposed to explain how this works. So I'm a bit short on time, so just a hint. So these two flies argue, and then they decide to walk away from each other, and this one walks away in this direction here. This one walks away in this direction, and they don't want to see each other again, so they walk in a straight line. But because the apple is curved here and there's this thing, it turns out, although they always walk in a straight line, they meet again. Right? And this is how it's the curvature of the surface of the apple, which makes the two flies come together again. But when they look back, they see, oh, there's an attractive force that has actually forced us to come back together again. And that is exactly the same force the Earth feels. When you're at the Earth, you see, oh, there's the Sun in the middle, and there's an attractive force. But actually, no, it's space-time that's curved. Okay, so that is a background. Now imagine we build even bigger particle accelerators. So big, so here is my proton, here's another proton. I throw them together. But now I want to look at so small structures, and I crank up the energy to such a degree that this energy that comes together in the collision is so strong that the gravity of this energy is relevant. And in fact, it curves space and time, and it curves it so much that you produce a black hole. You produce something that curvature is so strong, nothing, not even light, can get out. Right? So I produce a black hole. And that means I try to look at something very small, but I can't see it. Right? Because there's the black hole. Stuff disappeared in the black hole. I can't look at it. And it seems like there's a fundamental limit on how small things I can see. That's very important. So, because when you try to look at smaller things, the curvature of space becomes so strong that it hides these smaller things. So you can even argue that maybe there are no smaller things. It doesn't make sense to ask for smaller things because you cannot look for it. Right? And that is the problem that underlies the theory, the cloud of theories called quantum gravity, because what's important here is you have both quantum physics, which does the particle collisions, and gravity, which makes the black hole at the same time. And whenever you bring quantum physics and gravity together, you cannot avoid this problem. You have something drastic happens, there are further limits to what you can look at. And it doesn't make sense to talk about shorter distances than the typical scale at which this happens, which is 10 to the minus 33 meters. And just, I mean, it's always hard to have an idea on powers of 10. So remember there was the proton is 10 to the minus 5 meters in diameter. So you take 1 meter, scale it down to the size of a proton, and then you scale it down for another time the same factor, then you reach this. So it's completely, I mean, out of reach for experiments today at least. But theoretically, it's an important thing to look at. And that's my area of expertise. So the most promising, as far as I'm concerned, and I would say most of my colleagues, the most promising approach is called string theory, and the idea is very simple, and that is actually the different particles are not different particles. Well, first of all, if you look inside them and what they really are, they're not point-like. I mean, I've drawn them here like big chunks, but I mean, they have 0 diameter. But they're made of little rubber-type strings, and what this string can do, it can vibrate. So I've drawn here 3 different vibrational modes, and what looks like 3 different particles are actually just 3 different vibrational modes of the one string. And the appealing feature of this very simple idea is, I mean, here I'm just talking about particles, and actually I'm talking about quantum physics. But when you do this, and you come up with this rubber band, and you look at what kind of particles you produce, you see that no matter what you do, you always produce something. Okay, you always produce something that is a graviton, which behaves as the particle that communicates gravity. So string theory, no matter what you do, always has gravity, and it's by construction it's a quantum theory. So string theory is a theory of quantum gravity, and it's the only known powerful, consistent theory of quantum gravity that we have. So the way this works is when there are these diagrams. So time goes up in this diagram. So 2 particles here meet and collide. They form 2 new particles. They come back together again, and they form 2 new particles. That's, I mean, the archetypical particle collision diagram. I mean, you not necessarily have 2. You have many, like you've seen before, but you can also have 2. In the string theory language, it looks like this. So you have 1 string, you have another string. They come together. Here they fly together. Then they join. They form just 1 big string. This disintegrates again into 2, 1 here, 1 here, and then they come together, and then disintegrates again into 2 strings. And what you see in this picture, I mean, this is the same picture as this, just from the stringy perspective. And what you see, I mean, the important thing about this is this diagram has special points where stuff happens, namely here and here, right? There are old particles forming new particles. This does not happen here. I mean, here, any point on the surface is just as any other point, especially the point here where I pointed when I said the stuff comes together. You just rotate this thing a little bit, then it's not this point, but maybe it's this one. So this point, when you look at it closer, is just as good as this one or this one. Okay? And that is a conceptual big advantage of string theory, because you don't have to explain how this works. You just have to say string, and it's all built in. You just say how this little bit here works, and then all these interactions are already built in. You have no freedom to decide. Okay, one last thing about is extra dimensions. So I have to say there's one big disadvantage of string theory, and that is string theory wants to live in 9 + 1 space-time dimensions, although we only see 3 + 1. So we have to get rid of 6 dimensions. So it looks like this theory is complete bullshit, right? But it's not, because there's this thing you can do that's called compactification, and that tells you when stuff at big scales look like it has certain dimensionality, it can be wrong at small scales. So for example, there's again our friend the fly sitting on some sheet of something. So this is something 2-dimensional. But actually, the 2-dimensional thing is the surface of some pipe, right? And when you zoom out, when you go to bigger scales, it looks like this. I mean, I've zoomed up the fly, but this is now something one-dimensional. But the idea is when I go back, something one-dimensional can actually be two-dimensional when you zoom in. Right? And the same thing happens in string theory. Okay, here, cat content, but you're supposed to look at the carpet. So this Flickr carpet, when you're far away, looks two-dimensional, but when you zoom in, you see actually there's the wiggly stuff. It's actually three-dimensional, so it's one dimension higher. Okay, so the string, now you do the same thing, just with at each point in space-time, when you look at it closer, there's something six-dimensional. There's this archetypical drawing of something six-dimensional. It's of course not six-dimensional. The drawing is even something two-dimensional. But everybody thinks this is how six-dimensional stuff looks like. So that's the idea of the compactification. And the problem is, I can talk about this, but there's not a unique way to do this compactification. There are roughly 10 to the 500 ways to do this. And unfortunately, our particle physics, the types of particles, I've shown you the types of particles we see. The exact details of these particles are determined by the choice nature made for this six-dimensional space. And since there are many possible choices, even though the string theory by itself is unique, the way the compactification is not. And that means the so-called low-energy physics, so the particle physics that comes out of it, that we see at our scales or at LHC, there are roughly 10 to the 500 possibilities. So it's not very predictive at this scale. But when you zoom in such that you see the 10-dimensional nature of space-time, then it's unique. So this question of whether you can measure string theory or not really hinge on the question whether you think it's, at least in principle, possible to bring up such high energies that you see the 10-dimensional structure. So that's the end, so I had to include a cartoon as well. Yes, science is an open process in which a good idea can come from anybody. Yes, widely believed theories are on occasion overturned by simple thought experiments. And yes, your philosophy degree equips you to ask interesting questions sometimes. But you do not just overturn special relativity, a subject you learned about an hour ago, with your race car on a train idea. You just don't like that I'm turning a rational eye on your dogma. Hey, what's the email for the president of physics? So this is my last slide, which is about open source physics. So what do I mean by this? There's a conflict, right? So everything that we do is open. We publish everything in the open. You can go to www.arxiv.org and dig up all the order of 20 to 30 papers we write every day about string theory, and you can read it, and you can read about the data that they measure at LHC. You can even download, the data in the cosmology, in these cosmology pictures, you can go to NASA website and download. It's about 3 megabytes of numbers, and you get the numbers that produce these plots. And you can do your own physics there. So it's open in a sense. Everybody can do it. On the other hand, it roughly took me 10 years to learn this. To a level not that I can present pretty pictures, but I can do calculations. And that's the problem here. So of course, you're all welcome to join us. But unfortunately, you probably need more than half an hour. But still, it's open to the scrutiny of everybody who's ready to invest a significant amount of time. But you have to invest this time, because I also want to say that, my colleagues and I, we're getting emails from people who came up with their private little theory of why relativity is wrong or why string theory is obviously bullshit. And they got this idea from looking at these pictures. But I have to show you, it's a bit more, there are formulas behind these pictures. And I think it's the most interesting thing in the world you can do, but it needs some investment of time. But this is like in every non-trivial thing. Okay, thank you very much. We have like 1, 2 questions. So, microphones are there, you know this for day 4.
Right, I would ask anyone with a question to line up on the microphone over there, please. Short question.
Okay, I'll be outside if you don't catch me here.
Great.
Okay, there seems to be one question. Hi. Shoot.
Yep. So you said that physics was an open source process, more or less, because data was freely available. But when I try to download scientific papers, I often end up on websites like i3, SpringerLink, ICM, and they ask me to pay for a subscription or to pay for the paper. What do you think of this?
This is evil.
Yes, it is. I agree with you.
Yeah. I mean, I could give it completely another talk about why Springer and Elsevier are evil. But I can assure you, we put all our papers in our community, we put them all in open access places so you can access them for free. And you can also upload your own papers there.
One short last question, please.
Yeah, another question. According to Einstein, the curvature of time and space depends on the mass of an object, and thus influences the mass of an object influences the curvature of time and space. If time and space are inherent properties of space of the universe, why do we need a gravity propagating particle? And is there a time propagating particle?
That's a different formulation. It's actually equivalent. I mean, you can explain the same thing with the curvature with a propagating particle, but the propagating particle is the more convenient language when you also want to talk about high energy physics and quantum physics, but it's equivalent. Okay, I
Right,
think we have to close here, right?
Right, we're
So
at the end.
people need this room, so I'm happy to answer further questions outside.